Hello, how's it going everyone? Professor McMath here, back for another exciting video. This time we're going to tackle the amazing concept of exponential equations and inequalities and how to solve them. So we're not quite done with equations yet. In fact, we're never done with equations. Equations are going to be life. Hashtag equations life. So, first thing up, solving exponential equations. So, to solve an exponential equation, we need to get the base to be on both sides of the equation to be the exact same. And then we can then set the exponents equal to each other and solve that out. Now, there are exponential equations where we cannot do that. It's physically impossible. That's like in the case where we have like a 2 to the x equals 10. Because 2 raised to any integer power is never going to result in a 10. That is the second part of this particular unit. We're talking about exponentials. We're also going to talk about these ideas called logarithms. And that allows us to solve something particular like that, besides a guess and check model, obviously. So again, the key is, though, we'll have stuff like 2 to the x equals 8, 3 to the x equals 27, things that we can rewrite them as the same base. Once the base is the same, easy. You just set the two of them equal each other. So, 2 to the x equals 8 to the third power. Well, 2 can't go any smaller. That's as far as I can go there. However, the 8, I know 8 is 2 to the third power. So 8 to the third now becomes 2 to the third to the third. Which means we now have 2 to the x equals 2 to the ninth power. Well, once the bases are equal, we essentially, though not really, cancel them out. Again, we're not really canceling any bases. That's not what's happening here. But we can essentially ignore them and go, okay, the bases are the same, whatever. Look at the exponents. X equals 9. Now, if it's straightforward like just x, we're done. If that's more of a linear equation, like a 4x plus 3 kind of situation, then we actually got to solve it out and really get an answer there. But that's about it. If you like, you can go ahead and plug it back into a calculator. Check it out. We have 2 to the ninth power. Come out to be 512. 8 to the third power also is 512. Golden, we're good to go. Alright, so we could have situations where we have our exponentials and the exponent has a variable in both spots. Well, we still rewrite them. 9 and the 3 are my bases. Well, 9 is 3 squared, so let's rewrite that one. So 3 squared to the 2x minus 1 equals 3 to the 6x. This becomes 3 to the 4x minus 2, remembering that, again, we multiply exponents to each other when they raise powers to powers. Well, now we have the same basis, so again, don't need to worry about it anymore. We just got the exponents left. 4x minus 2 equals 6x. Sweet. So now we're going to go ahead and move the 4x over by subtracting. Get negative 2 equals 2x. Divide by the 2, x is negative 1. Again, you're welcome to plug that in to try it out. If we do 9 to the negative third power, that's what happens when you evaluate 2 times negative 1 minus 1. We'll get a 1 over 729. 3 to the negative sixth power is also 1 over 729. Great. Now, what happens when we have a situation like this, where we notice 16 and 8 I can't rewrite 16 as 8 to a power, I can't rewrite 8 as 16 to a power. What do we do? Well, we look further. Do they have anything that they both can be written as that they have in common? Well, 16 can be written as a 4 squared. Not going to help me because 8 is not 4 to a power. But 16 is 2 to the fourth, and 8 is 2 to the third. So I can rewrite it that way. So we might have to use both numbers to get a common base. So again, 16 is 2 to the fourth. So we'll have 2 to the fourth power to the 3x plus 1. That must equal 8, which is 2 to the third, to the 2x minus 1. Well, now I'm going to get 2 to the 12x plus 4 on the left-hand side, and then 2 to the 6x minus 3 on the right-hand side. Bases are the same. I got to go ahead and ignore them. 12x plus 4 equals 6x minus 3. Move the 6x over to get 6x. Subtract the 4 over to get negative 7. Divide by 6, and x equals negative 7/6. Again, you are still more welcome to plug it in to check it out, but I think you can trust me at this point. I think we're going to be okay with that number. Alright, so that's the idea behind solving an exponential equation. Now, if you remember back to, the title of the slide, it said exponential inequalities. Well, how do we solve an inequality? Well, like any inequality we've ever pretty much encountered that we are going to be dealing with, we're going to solve in the same manner. We want to just simply rewrite both of them as the same base, and then now instead of saying the left exponent equals the right exponent, we say like the left exponent is greater than the right exponent, or left exponent is less than or equal to right exponent. Whatever it is, we just have an inequality sign instead of an equal sign to solve it out. So we have an 8 and a 16 as our bases. We already saw this previously. So we know this is 2 to the 4th power, so 2x minus 3. And this is then less than 2 to the 3rd power. Well, we get 2 to the 8x minus 12 is less than 2 to the 3rd. So now I ignore the bases, and now I say 8x minus 12 is less than 3. We keep the inequality sign the way it is. We only flip it around if we divide by negative, so don't forget that key fact. Add the 12 to get 8x is less than 15. Divide by the 8s, x is less than 15 eighths. So if you plug in a number like 1, for example, this will work out fine. If you plug in a number like 0, negative 5, negative 20 trillion, anything less than 15 eighths is fine. If you tried 2, though, 2 would not work. If you tried anything that was bigger than 15 eighths, like maybe, what's 15 eighths? It's like 1 and 7 eighths, so it's 1.875. So if you tried like 1.9, not going to work. Anything like that has to be less than 15 eighths. And then, oh, well, look at this. We got a fraction in the problem. Everyone's least favorite number. No big deal. We're okay. Fractions are our friend. Fractions are okay. We gotta take a look at this. Okay, so if we have a fraction with exponents, what we need to remember is we need to think of this as a negative exponent. So ignore the 1 part. Look at 32. Can you think of 32 as a 2 raised to a power? Well, hopefully you were thinking of 2 to the 5th, and that would be correct. 2 to the 5th is 32. Well, then that also means then 2 to the negative 5th is 1 over 32. Because the negative exponent rewrites it as a fraction 1 over whatever it is as a positive exponent. So that's what's happening here. We're saying 2 to the x plus 2 is greater than or equal to 2 to the negative 5th power. So again, anytime you've got a fraction in the problem, ignore the numerator 1 for a second. Think of the base. Okay, can I rewrite that base, that bottom, as the opposite base? Great. If you can, use a negative number instead of a positive number. That's all you got to worry about. Well, now we solve it out. We have x plus 2 greater than or equal to negative 5. Subtract the 2. X is greater than or equal to negative 7. So any number you want, as long as it's bigger than or equal to negative 7, we're going to be golden. We're going to be okay. Alright, so last thing we're going to talk about now is actually applying this a little bit. So we're going to talk about solving compound interest problems. We have this compound interest formula. A equals P times 1 plus R over N to the NT power. So we got a lot of variables in here, so we got to talk about these. The A value is essentially our final amount. It's what's in the account after T years. So if we have the account going for 10 years, whatever you've got left over in there, that's A. P is the principal amount. It's what we call the starting amount, the initial amount. So if we initially deposit $100, we initially invest $2,000, that's our P value. R is the annual interest rate. It has to be an annual interest rate, so if they tell you it's a monthly interest rate, we need to then make sure we divide that by 12 for an annual interest rate. And it also has to be written as a decimal, not left in percent form. And then N is the number of compounding periods each year. Now, what a compounding period is this. So if something is compounded monthly, that means the interest is applied every single month to what the balance is. Whereas if I say it's compounded yearly, it's just going to accumulate the money and then it's only going to apply the interest at the end of 1 year. So in a monthly case, well, there's 12 months in 1 year, so N is 12. If you're not using 12 for N in a monthly case, I would like to know what calendar you're using, because clearly you're using something different. If we say it's compounding quarterly, that's a common phrase you'll see in business and finance. Quarterly would be 4 compounding periods, because there's 4 quarters to the year. You could see something as twice a month, in which case it'd be 24. It'd be something that's compounded daily. Where if it's anything that's ever compounded daily or weekly, we're assuming it's the 52 weeks in the year, 365 days in the year. We're not assuming that it's like, well, technically it's 365 and a quarter, so a leap year it's 366, or a week is like, well, technically there's 52 weeks and there's a little bit of change. No, we just assume a nice whole number measurement right there. So it all depends on the scenario and what's actually given to us for the problem. So, an investment account pays 4.2% annual interest compounded monthly. So there's my R value. Only as a decimal, it's 0.042. Can't leave it as the percent form. $2,500 is invested into this account. That's our initial amount. That's our principal amount. That's P, $2,500. It's compounding monthly, so that means N is 12, because there's 12 months in the year. They want to know what would be the balance after 15 years. Well, T is 15, and our A value is unknown. Well, so we're going to say A equals 2,500 times our, let's see, it's 1 plus the interest rate, 0.042, divided by compounding 12, and then the exponent's number times compounded times the number of years we're compounding it for. Something like this you want to put into your calculator all in one step. So pretty much how it's written out, 2,500 times with parentheses, 1 plus 0.042 divided by 12. And we raise it to the power that is 12 times 15. Make sure the 12 and 15 are both in the exponent position. If you want to separately multiply 12 and 15 and then use that number as your exponent to ensure you're not raising to the 12th power and then multiplying the result by 15, do that. Either way, your final balance, and since we're talking about money, we're going to round to the hundredths place, will be $4,688.87. Exactly, it's 4688.866166. Again, money, we don't carry anything past the hundredths place, so that's why we round the first 6 there up, because the number after it is also a 6. So that's one type of compound interest. You're given everything besides the final amount. What is the final amount? The other type of compound interest, which we'll talk about at this time, because there's plenty of others, is where you're given the final amount and want to know what is the initial investment. What was the initial amount there? So here we're told after 20 years, so when T is 20, we have an investment of exactly $6,000 that's left over. So 20 years, our final amount is $6,000. The annual interest rate was 1.2%, so it's 0.012. And we're told it's compounded twice a month. That means it's 24 times in a year. And we want to know what was the initial amount, what was our initial total there. Well, so it's a slightly different setup. We'll say 6,000 equals P times 1 plus 0.012 divided by 24 to the exponent of 20 times 24. So there's a couple different ways you can look at this. You should be able to, in one step in your calculator, since to solve for P, we'd have to divide by this large number right here, or this large expression. It's not necessarily a large number. So we're dividing by the expression 1 plus 0.012 divided by 24 to the 20 times 24, which is actually 480. We'll just do that to make our lives a little bit easier. We can just divide by that in just one nice step. So 6,000 divided by 1 plus 0.012 divided by 24 to the 480 power. So we're apparently getting an initial amount of $4,720.05. Which kind of makes sense. We have a very tiny interest rate, so that's, even though it's been 20 years, we're not really going to get a lot out of that. That's why it's important if you start using this idea as like retirement, which is compounding interest over and over on a monthly basis, you kind of want to make sure you're constantly putting money into it. That way it's going to grow a lot from there, and eventually, once you start having a high enough value in there, the interest rate will actually, even if it's low, really do something for you. Alright, so those are your two situations we're going to deal with right now for compound interest. We're not going to discuss possibilities where we don't know the R value, or we don't know the T value, we don't know the N value. That's not going to be a relevant case for this particular scenario yet. We'll focus more on either not knowing A or not knowing P. Alright, that's all I got for you today. That's all I got for you on this particular video. Hope you enjoyed watching. I certainly enjoyed doing this. And then we're gonna take a look at some more stuff. We're gonna talk about logarithms, talk about some more exponentials. It's gonna be a good time. So, McMath out.